Hello again, welcome to the wasting time portion of the coding train. My name is Dan Schiffman and I have about 40 minutes before I have to go. I just finished an hour of code tutorial, and the camera of course just shut off, where I made this project that tracks your nose. It tracks your nose with P5, ML5, and the PoseNet model, and I'm here now to waste your time. Because I have a bunch of things I want to experiment with and discuss. But you should probably just go about with your day. And if I can manage to get a coding challenge in before I go, I would like to do that. So one thing I want to test here, and I don't know why this isn't working. Well, let me try refreshing this again. All right, so I'm planning, by the way, it's probably going to be December 20th. I am planning a fundraiser for the Processing Foundation, processingfoundation.org. If you're not familiar with the Processing Foundation is the non-for-profit entity that manages the processing project, P5JS, processing.python, and also a lot of community and education initiatives around art and code and all sorts of stuff. So read the mission statement, come hang out with us at any number of processing days around the world, which is happening in 2019. And I will be at Processing Los Angeles and hopefully at Processing NYC as well. All right, that aside, I wanted to figure out, I have this, Processing is a 501c3 non-for-profit, and this setting, I don't see it. I wanted to enable Super Chat for Good to see if I can figure out how to get live donations, and then I can also build something which actually shows the live chat. But maybe what I first need to do, hold on. So what I'm doing over here is I'm in my admin panel. And maybe I'll just build something that manually pops up something when there's a super chat. But why do I not have, I'm going to live streaming. I'm going into events, a live edit. There's 214 of you apparently watching right now. And under advanced settings, under chat, it's not there. So I used to have an option that was Super Chat for Good, and I could enable the Processing Foundation. So never mind, I wanted to test that now. I'm gonna have to figure that out and test that another time. Oh, look, it's me with googly eyes. Thank you to Bruno Ruchiga, who made this wonderful sketch. All right, so let's close all this out. The other thing that's goofy, okay. So I don't know what to do now. Hello, how are you? Hopefully that, yeah, I should make, you know what I should do for the fundraiser is on the fundraiser, I should write a P5 sketch that communicates with the YouTube API and like makes a little like heart or something whenever somebody makes a donation. But I need to get that Super Chat for Good thing working. Okay, so if anybody knows about, I mean, I'll contact YouTube, but if anybody knows about that or has worked with the YouTube API, actually, I know you can write bots and things for the chat. So that's actually probably what that's something I should look into and do. So what can I do right now? I have a 35 minutes. I had this idea actually, this is probably insane to try to do this, of doing like a flocking simulation. Let's go to Coding Train on GitHub. Why am I not signed in? I'm going to need my authentication here. Let me look up the authenticator. Oh, I'm streaming and recording? So weird. And go down here. Hit sign in. Oh, no, that's not my password. That's my, Now, Everybody knows my authentication code, but it's already gone. All right, let's go here. Only 871. 871 ideas. Regarding your previous stream, if you define a 2D shape in relation to the points, surely you can in 3D as well. Yeah, absolutely. All right. Now, I have no plan. None whatsoever. Schrodinger equation. Create a gaffing, revisiting pixel sorting. Oh my God, with the quick sort. Oh, I would love to do the quick sort coding challenge right now, but I don't think I'm going to. Triple pendulum. Chain reaction. Marching cubes. Ooh, that would be a good one. Stolen necklace. Drunken bishop. Spiral map projection. Coding challenge. Maybe what we could do. You know, I have this like weird idea that I would like to do, which is because I was watching a stand-up maths video on unboxing this DVD, and it was like this crazy infinite recursion into the TV thing. I feel like we should just program that. That would be fun, because I was doing video stuff. But I don't know. Plotter, soft body simulation, Roman numerals, clicking on an object in 3D space, lizard visualization. What is that? Of a movement of a lizard. The lizard should have a triangle-like head, body, legs. It should go to the point where this is very specific. It should go to the point. It should go to the point where the mouse was clicked. The hard part will be the way the lizard moves. It should turn and move at the same time and travel the least distance. Ideally, when the lizard is facing one direction and when mouse is clicked, it should start moving like a real lizard to reset point. Okay. I don't think I'm going to get to this right now. So I don't know why, but in my head this morning, I thought I should do the flocking as a coding challenge. Boid's challenge. Look, I even assign this to, no, there's no thumbs up on this one. I'll give it a thumbs up. Could this be done in a half an hour? That's the question. Why? Come on, GitHub. Come on, computer. Let me refresh the page. It doesn't even want to let me give it a thumbs up. There we go. How many thumbs up? How many thumbs up can I get on this page right now? I'd like to see clock at Destin. His name is Destin. Destin's office from Smarter Every Day. I don't know about that clock from Smarter Every Day. But I'm always interested. Oh, right. Do weird complex number math on the image to make that spiral pattern in Matt Parker's videos. I want to do some like fluid dynamics stuff, because I have been watching a lot of the Smarter Everyday videos about shock waves, and I think that would be an interesting thing to do, like a shock wave visualization. Oh, I think that. No, nobody's thumbs upping this. Just me. I'm the only thumbs up emoji. 2, yes, all right. Come on, everybody. By the way, this is my live stream for, if I can get that to 10, I'm going to do it. This is my live stream for the week. Tomorrow, I'm actually doing some school visits for Hour of Code, which is going to be fun. We got to number 5, number 6. And what I wanted to say, by the way, I am planning, oh boy, what is number 9. All right. Woohoo! Are there any? Oh, let's check if there's any Coding Faces tweets. And please, I'm just going to, I'm now always afraid. I'm afraid of the internet. So I'm going to the Coding Faces page. Oh, look at this. We have got some. You've got one from Carol. Oops. Here we go. Carol posted, Carol at DERKAROL on Twitter 3 minutes ago posted my first ML experiments with coding faces. Awesome. What number are we at now? 15. Okay, oh, 2 thumbs down. No, don't thumbs down me. Oh, look, I will make my sad face emoji. Oh, sad face emoji if you thumbs down me. I'm confused. I'm confused by your thumbs down. Oh, it's so sad. Oh, look. Oh, the hearts. Look at this. This is really like wild to me to see this happening in real time. 22. Oh, people are watching. All right, but I have to go. I have a meeting to be at. Do we think we could do the flocking? All right, let's get prepared. We'll check back on coding faces. Let's get prepared to do this. So flocking video, Schiffman. Let's see if that comes up. Ooh, look at this, interesting. Let's go Craig Reynolds, steering. No, not videos. Ooh, original 1986 Boid simulation. Oh, awesome. I want this page, Boids. Here we go. And then nature of code. Read now. Autonomous agents. Here we go. Well, those diagrams are better. Here we go. Here we go. Okay. All right. Flocking. Okay. So I've got my references. I have got and here. And we're going to do this. I think this requires, I don't want to do this in the web editor. I think there's too much involved with the complexity of this that that I think what I want to do is use I'm just going to run my own server. With a console. And I am going to, I already have the code editor open. I'm going to get rid of this. And someday I'm going to make myself a little template here. But today is not that day. I need the CDN. And let's, just in case I need the DOM library, let's get this. And sketch.js. Let's just give it a fixed size, background, 51, and what's going on here? Oh. No? Oh, did I reset the browser? I think I reset the browser here. And yeah, this is not selected anymore. There we go. So now this can be minimized. I don't need that open. I don't need this open. And don't save. Don't save. So, and then here, this. So how am I doing? I'm standing here, that's good. So I'm not in front of the code. So I can actually do this a little further over. Okay, how's that font size? And I've got this here, which can actually also be over because it can just be above me. There we go. And let's have more room in the console. Okay, perfect. All right. 32! All right, we're going to do the flocking the Boids challenge. This is definitely going to take longer than a half an hour. This is a really complicated project. Simon, yes, I know I haven't redone the beginner P5 tutorials. I think I need to schedule a time to do more of those. Okay. So let me actually just go to oh, this is what I'm looking for, by the way. Here we go. All right. Why is that so slow? Let's open up processing. Oh, shoot. Sorry, I'll play some music while I'm waiting here. Oh, actually, I think it's in here. Oh, so slow. Okay. How do you do that? Unnecessary. Okay. Sorry, everybody. Sorry, I'm trying to put an image behind me that'll be interesting. It's like I'm spending forever tweaking this, which is really wasting time when I should just be coding. All right. Okay, I think I'm ready now. Okay, the house, I'm definitely going to need the whiteboard. So let me erase that. Okay. Let me just send a quick message here. Let me just send a quick message that I need to send. Sorry, hold on, because I'm going to probably be a little late. Okay. All right. Close enough. Close enough. Oh, I should get some water, but whatever. We're gonna move forward with this. Let's just add like a few more and make them, they're too big. Let's make them a little bit smaller, and let's make this like that. Okay. Oh, perfect. Now it's perfect. Okay. Hello, welcome to a coding challenge. In this coding challenge, I am going to attempt a program using the P5 library, starting from no code, except for the, just give me one more chance. I have this like hang up where when I say from scratch, people are always in the YouTube comments, well, it's not actually from scratch because you've used in the P5 library. Oh, you know, what can I do? Okay, here we go. Hello, welcome to Coding Challenge. I am going to, in this coding challenge, make this. This is a processing sketch. I need a random number. I need to read a random number. Move the mouse out of the way. Yes, thank you. Okay, good, thank you. 72475. Okay, I have a random number. Everything's going to be fine. Let me cycle the camera. What's the chance that I can be done in a half an hour? Very, very little chance. Well, I also haven't eaten lunch. This is not going to go well. Hello, welcome to a coding challenge. In this coding challenge, I probably should go eat lunch, but I'm going to just try this coding challenge. I am going to attempt to program this. This is a flocking simulation. What you're seeing right now is an example that I made many years ago of a flocking simulation, a Boid system running in processing. So I'm going to try to make exactly this, or close to it, in JavaScript with the P5 library, starting from no code at all. You know, obviously, besides the dependencies. Okay, so this is the example running. So let me just give you a little bit of background here. If you want to learn more, about the flocking algorithm as invented by Craig Reynolds, you can go to this link to read this explanation of it. And find many other links and resources down here. Whoa, that's a lot of stuff. Have fun. See you in a few weeks. You can also check out this YouTube video of the original 1986 flocking simulation. Wow, that's amazing. Oh, this is so cool. Oh my God, I love that. And you can also find an explanation of it as part of my Nature of Code book online with some diagrams and code written in processing and an exercise that you could try, which I'll refer to back at the end. But I am going to start from this, a blank slate. I just have a canvas. It has some amount of pixels in it. There is nothing happening in the console. And I've got this code, set up and draw. All right, so what do I need to do? Now, there's definitely going to be a big need to refactor the code that I'm going to write. So if you look at my example, it's hopefully somewhat well organized, but I'm going to thank you, Mathieu, for editing for me. All right, let me double back for a second. So I'm going to write this code without worrying about being like perfectly organized and being able to scale it very easily. I just want to try to get the algorithm working. But of course, where is the button? And if you want to see a refactored example of it, you probably could go and look and actually at my finished version in the Nature of Code, which I'll also link to. So the first thing that I want to do, though, is I want to add another JavaScript file called particle.js. And actually, you know what? I should rename this to Boid.js. So what is this term Boid? When Craig Reynolds invented this algorithm for simulating a flocking system, like a flock of birds or a swarm of bees, I suppose he didn't want to use the term bird, but it is kind of like birds, so Boid. It's kind of like droid, but Boid. Go read the original paper about steering behaviors and flocking systems, and you'll find out more about the history about this. But I am going to make a class called Boid. And I am going to use the P5 vector object. And so I'm going to make Boid objects. And each time I made a Boid object, I need a constructor. And I am going to give each Boid a position. I'm going to give each Boid a velocity. And I'm going to give each Boid an acceleration. And all of those are going to be vectors. So I'm doing this in 2D. You should, after you watch this, if you watch this, you should make your own 3D version of this. All the math will work exactly the same way, but you'll just need to rethink how you're visualizing this. Just to give things a start, let's just put the position like in the middle of the window. And let's write a function called like show, which will just draw them as a circle right now. Actually, I'll just even use point, like stroke weight 16, stroke 255, point this dot position dot x. Oh, I think Visual Studio Code will do this for me. No. Where does it? It fixed that for me once. I had that enabled. Whatever. OK, so this dot pointer event. Well, I'm not a pointer event. I'm a point. OK, so now if I were to then here make a flock, which is an array, and I probably should make a flock class. That might be a thing to refactor later. But I'm just going to say flock.push new Boid. And then I just want to say for every Boid in the flock, and I'm using a for of loop, but I said in because that's the way I feel right now, Boid.show. And then I need to make sure I am also referencing Boid.js in my index.html. So I have the basic Boid class, which just creates a position, velocity, acceleration, and draws it as a point. And then I have my sketch where I make one Boid and I draw it in the center of the screen. There it is. There's my Boid. Step one complete. I probably should plan this out, but I have one Boid. That's good. Now, let's have that Boid move. So let's actually write in the Boid object a function called update. And this I probably covered ad nauseum in a lot of other videos in my whole Nature of Code series. But the idea here is that position is updated based on the Boid's velocity, and its velocity is updated based on the Boid's acceleration. So if I now actually create a p5.vector random 2D, believe this is a function that will give me a random velocity vector, and I now go in here and say Boid.update. OK, cannot read property add of undefined. This dot's on. No, I have the this dots. Oh, I just spelled it wrong. I thought I missed the this dots. OK. There we go. Look, it's moving. It's moving with a random velocity each time. OK, now let's just make a bunch of these. Now I have a system of 100 Boids. And interesting, look at this. It fans out in this purple perfect circle. Do you know why that is? Because I make a Boid and I give it a random velocity. That random vector is always of unit length 1. The direction is something different. So they're all actually moving with the same speed. If I wanted them to have, and this is not an important detail to the flocking stuff, but just to sort of get a sense of how this vector stuff works, I could say this dot velocity set mag, which is set the magnitude to a random value between like 0.5 and 1.5. And now you can see now they're all moving with a slightly different velocity. So this is, by the way, a nice little almost like explosion motif, and I could have them with a real big burst and they slow down. There's all sorts of physicsy stuff I could do with this, but I just want to do flocking. So how do I do flocking? Let's return to this paper here. This is the key behind Craig Reynolds' flocking algorithm. 3 rules. Separation. Steer to avoid crowding local flockmates. Alignment. Steer towards the average heading of local flockmates. Cohesion. Steer to move toward the average position of local flockmates. Something so crucial in that description is the word local. 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 What does that mean? So let's just do, I think the easiest one to do actually is alignment. Let's do alignment first. So alignment. Let's make our own diagram. Okay. So let's say there are 5 Boids. Actually, let's make a lot more of them. These are all of my Boids. This is the one that I'm currently operating around. And it has a velocity vector like this. Let me just make up, let's just pretend like the ones around it are kind of moving all in the same direction, because that'll be easier to think about. So this is the current one that I'm looking at. So, and maybe some of these others are also moving in other directions also. I could take the approach to say this particular Boid needs to align itself to everything. But this is not really how complex systems in nature actually work. The emergent phenomena comes from this Boid having a limited perception of its environment. So maybe it's actually only able to see things that are in front of it or behind it or to the right, or what's probably the simplest thing to implement is within some radius. So I only want to look at the Boids that are within this radius, meaning this one, this one, this one, this one, this one, this one. So what if I iterate over all of these ones that are within some distance, average all of their velocities, and shift this velocity in the direction of all those velocities? That's what we want to do. So I am going to write a function now. I'm going to put it in the Boid. I'm going to call it align. And it's going to get, presumably, an array of other Boids. Like the idea is this function align this Boid with all the other Boids. So what do I need to do? I'm going to make a variable called average, which is going to be a vector. Then I am going to iterate over, and I could do all of these with like reduce probably in some higher order array functions. That's a great thing for you to refactor it later. But I'm just going to do it this way. I'm going to say, I'm actually going to use I, because that's maybe going to help me. I'm not really sure, but I'm going to use I right now. Actually, no, I'll still use a for of loop. Let other, I'm going to call it other of Boids. And I'm going to just say average.add other.velocity. So I'm adding up all of the velocities. This is how you do an average, right? Vectors, right? Again, you might want to go watch some of my videos about how vectors work, but a vector, a P5 vector, just holds an x and a y, or an x and a y and a z. So if I want to average the vector, it's represented as an arrow with an x component and a y component. If I want to average it, just like I might average an array of numbers, I add them all up and divide by the total. And then I would say average.divide by Boids.length. This would be a way of getting the average velocity of all of the Boids. But remember, I only want the ones within some distance. So actually, let's implement that right now. Let's have some sort of distance like max, or I'll call it like perception, equals, let's just make it sort of arbitrary like 100. And then I'm going to now say if the distance between this dot position dot x, You know what? I think there's a P5. This is fine. It's just going to be, it's kind of long the way I'm writing this, but I don't mind. If the distance, let's actually make it in a variable. D equals the distance between this Boid's position and the other Boid's position, x and y. And if that distance is less than 100, ooh, look at that. Look at this fancy thing that it's doing. I have some like prettier stuff that like doesn't want to let me write a long line of code. I guess I'll keep that in there for right now. So I'm calculating the distance between this Boid's position, the other Boid's position, and if that distance is less than 100, I'm adding it up, and I should also probably have a total number. Total equals 0, add it up. I also should probably ignore myself, and if other does not equal this, right? So I basically, and I might as well put that first, right? As long as the other thing is not me and the distance is less than 100, add it up and then divide by the total. But obviously I only want to divide by the total if total is greater than 0. All right, so this is kind of a little bit of a long-winded algorithm now, but and perception. If D is less than perception. So, okay, I'm starting with a perception, a radius of 100. Maybe that would be better as I call it like perception radius. That's really what it is. I'm starting with a perception radius of 100, an empty vector. I'm adding up the velocities of any vector, any Boid that's near me, dividing by the total, and as long as I found one, dividing by that total. And you know, I probably should like run this to check this code, but I'm gonna keep going. So now here's the thing. I could just say, like, for example, I could do something weird. This would be really weird. I could just say this dot velocity equals average. Like, what if I did that? And then I said Boid, like here I said Boid dot align flock. And I don't know what's going to happen here, but let's refresh this. Right? They just basically don't go anywhere because they're all instantly equal to each other's velocity. So that's not really a good way. What I need to do now is, if I don't want to actually assign its velocity to that average directly, I want to steer towards it. And this is where Craig Reynolds' steering formula comes in. A steering force equals some desired velocity minus the current actual velocity. It's kind of like the error, right? If I am moving this way, or if I'm moving this way, but I want to move this way, the way I'm moving minus the way I want to move is, oh no, sorry, where's my eraser? Desired minus velocity. The way I want to move minus the way I am moving is the steering force, meaning push me in that direction. So apply a force. Maybe I'm going to turn the steering wheel. You could think of these as bees or cars or birds or whatever. But this formula, desired minus velocity, will give me the steering force. And what is the desired velocity here? The desired velocity is actually that average. So I'm actually going to rename this to desired. And I'm going to add it up and divide by total. And then I'm going to say this dot velocity equals, no, I'm not going to say that. I'm going to say steering equals, and I can actually I should actually call this steering. Because I can do all this. I don't need to save anything as I'm going. So I'm going to call that the steering force. I'm going to add all the velocities. I'm going to divide by the total. And then I'm going to say steering force is the desired, subtract this dot velocity. And I'm going to say return steering. So I want this function to return that force. So really what I should be doing is I'm going to write a function called flock. That's maybe flock with some number of Boids. And then I'm going to say alignment equals align with those Boids. So I'm going to get this force. And I suppose okay, steering is here. So you know what? I should always return steering. So I want to always return a vector, but if it didn't find anything, I'll just return the 0 vector. And then what I'm going to do is I'm going to say acceleration add alignment. So the idea, the way that a physics engine works, and this has to do with, and this is like a very simple kind of crude physics engine, but force equals mass times acceleration. This is Newton's law of motion. Or acceleration equals force divided by mass, or in a world where the mass of everything is 1, acceleration equals force. So if I want to apply a force to this object, I just need to set the acceleration to that force. And actually, so that's what I'm going to do just starting out here. I'm going to say acceleration equals alignment. Okay? So now, if I go back to Sketch and I say Boid.flock Boids, we should now have all the Boids doing that one with just implemented with that alignment rule. Let's see. Boids is not defined. Sketch.js line 14. Oh, it's called flock. Oh, this is my variable naming is terrible. But I'm going to leave it that way right now. Align is not defined. Boid.js. Align Boids. Oh, this dot align. This dot align Boids. Oops. Acceleration is not defined. Oh my goodness. This dot, this dot, this dot, this dot, sorry. That's not much better. Okay. So let's think about this. So it's kind of working. Let me give them a much higher burst of speed, because I think. And all of them starting in the same place. Actually, also, let's do a couple things. Let me actually not have them all start in the same place, because that is, just to see this effect happen, let me actually start them in random places on the screen. So let me change that. Let me make the perception radius a little bit smaller. And I don't know why this matters, but let me draw them like a little bit smaller. Okay, so you can see, and let me actually have them start out going quite a bit faster. So you can see as they get near each other, they start to get each other's velocity. They start to average each other's velocity with their neighbors. And you can start to see these clumps moving together. Now, so much more to do on this. Oh, my goodness. Okay, but first, a couple things. One is I have now basically allowed these Boids to steer with like infinite power in a way. So like I'm saying, hey, your steering force is the difference between your desired velocity and your current velocity, and apply that directly to the acceleration. But if you think about it, if you're driving a car, in a car racing game, for example, there's this concept of handling, like how well can that car steer? So we should probably have a variable. We should probably have a variable. I'm going to call it max force. And I'm going to set it equal to 1 for a second. And then what I'm going to do is here I'm going to say steering limit this dot max force. So what this does is it limits the magnitude, the length of that vector to some maximum force. So this should be exactly the same, right? We're not seeing anything different. But if I were to make maximum force like 0.01, like really small right now, you're going to see like they're not actually changing their velocity. They are, but very, very slowly. And the other thing we're really going to need to do, I just have to like give up and do this. I'm going to add something for the edges here. So I'm going to say if this dot position dot x is greater than the width, this dot position dot x should equal 0. Else, if this dot position dot x is less than 0, this dot position dot x equals width. So, and then I'm just going to do that for the y. Why are you here? Why did the terminal open? I have no idea. I think I hit like a key command that made that happen. And then we're going to do this for y. And I could do this in so many different more thoughtful or refactored ways, but this is going to be good. Oh no, what am I doing? Ah! Okay. With x, x, y, 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 x, 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 with. All right, and now here, let's do Boid.edges. So we should see them reappear, wrapping around. And now let's go back to the Boid, and let's make this like 0.2 is kind of reasonable-ish. So interestingly enough, they're kind of like, it slows them down, which is interesting. But I'm only doing alignment right now, but you can see how this works, right? You can see they're all starting to align with each other. I could keep them going at some minimum velocity, which might make sense. So you can see how these are like kind of going back and forth. But you get the idea here, alignment. Why are they all slowing down? Is that just like a coincidence? One thing I could do is, this is actually going to be worth it because I should also give them a maximum speed. This is going to be a parameter of a variable that's going to allow me to control the system pretty well. And I could consider their desired velocity in the alignment to not actually be the actual average velocity, but just the average direction. Because I could then say steering.set magnitude to this.maximum speed. So basically I'm saying, like, I always want to go in the direction of my neighbors, but at maximum speed. And I don't know that that's really an important detail, but if I add that in here, we might get the effect that I was sort of hoping to get, which now, this is what I was expecting to see. As they get near each other, they're all starting to align together. Let me refresh that one more time. You can see that they're clumping, and as they group, they all start to align. So this is the alignment rule. This is a very simple rule. It's predictable. It's obvious. This is alignment. How many more rules do we have to do? Oh, and at one point I messed up the camera, didn't I? Well, whatever. Some fancy post-production thing that Mathieu can maybe do. Let me pause for a second. This is going to be an edit point. All right. Uh, 12:06. All right. Half an hour so far. All right. This is going to move faster now, I think. Let me cycle the cameras. Okay. So that is alignment. Woohoo! Alignment. Now, all we need to do is add cohesion and separation. So separation is going to be the hardest one to do. So let's do cohesion next. So same thing. We're going to look at our neighbors. We should go back to what the rule is actually defined as. Let's go back to Craig Reynolds' original page. Cohesion. Steer to move toward the average position of local flock mates. Okay, this is actually not going to be that hard because we've already calculated the average velocity of local flock mates. Now let's just duplicate that code, and I know we could refactor it. I won't play the song because we could probably do this all in one fell swoop. There's so many possibilities, but now I just want to get the average location of my local flock mates and steer towards that. All right, so the way I'm gonna do that is I'm just gonna go nuts and copy paste this whole thing and call it cohesion. And I'm going to keep the perception radius. I'm going to keep this idea of steering, keep this idea of total, go through all the Boids, check the distance between myself and the other ones, as long as they're not myself and within the perception radius. What am I doing? Steering at not the other's velocity, but the other's position. Then, right, so this should clearly be refactored into its own function, whatever. Then, as long as I have at least one, I'm going to divide by the total. Now, I don't want to set the magnitude to the maximum speed. So what I have now in steering is the average location. So if this is the average location, well, let's say it's over here, then what I need is a vector that's clearly not the average location, but let's just say it was. The average location is kind of like where this Boid is, but I want to steer in that direction. So to get a vector in that direction, I take the average location minus the current position of me, which is basically saying now what I want to do is say steering subtract this dot position. So subtract my position out. I have a vector that's pointing from me to the average location, which remember, which is in the steering variable. Then let's say I want to go at maximum speed. And then I want to, so this is now my desired velocity. I'm going to subtract out my current velocity, limit it to max force, and there we go. That's cohesion. So now in, where is that? In Flock, let cohesion equal this dot cohesion Boids. And then, oh, we have a big problem. This dot acceleration equals alignment. This dot acceleration equals cohesion. So how can I set the acceleration to two different forces? But before I even answer that, there's an easy answer to that question. Let's just comment out alignment, and let's watch cohesion happen. Right? We can see they start to group together. This is cohesion happening. And that neighbor radius, by the way, is a super important value. Right? That neighbor radius, if I were to change that, and I have a different, that perception radius, if I were to change that to like 10,000, right, they're all going to come together as one because they all see everybody. If I were to change that to 10, right, they're really, there's little pairs. Like you can see they kind of get in little groups of two. The force, though, isn't so strong. So like if I were to change the maximum force, right, to like 1, now you see them, they're almost like these little like electron thingies that like magnetic things that start to like spin around each other and then fan off. Okay. So there's so many possibilities here. I can make the maximum speed 2. Oh, I'm not actually limiting. You can see, there we go. That's what I was looking for. You can see they get into these little groups. But let me go back and say maximum speed is 4, maximum force is 0.2. And I realized this maximum speed is not actually a maximum speed because in update, if I really wanted it to be a maximum speed, I would want to say this dot velocity limit this dot max speed. So let's actually add that in and see what we get. This is, and let's put the perception radius back at 100. And there we go. So now we have cohesion. So we have cohesion. What happens if we have cohesion and alignment? How do we get cohesion and alignment? Okay, this is fun. I think this is really working. I'm excited. This is going to be a really long video. All right, cohesion and alignment. The problem rests here. This is actually a really easy thing to solve because this is called force accumulation. The answer here is force accumulation. In physics, if two forces are acting on an object, the resulting acceleration is the sum of those forces. So all I need to do is say acceleration.add alignment and acceleration.add cohesion, right? Because why is this not falling? Because the force of gravity is pointed this way and the other force of my hand holding it up is pointed in the other direction and with an equal magnitude. Therefore, it is at rest. Those two forces have a net, added together, have a net acceleration of 0. But obviously, so all I need to do is add them together. But there is this, if I actually do this right now, we're going to see some really crazy behavior. This looks like it's kind of working, but it really isn't. Because what it should also have is this acceleration shouldn't accumulate over time. At every moment in time, I start with a net acceleration, an acceleration of 0, and add all the forces together. So what I should do right before I flock is say this dot acceleration set 0, 0. This is setting its values to 0 and 0. Another way I could do that is just multiplying it by 0, because multiplying a vector by 0 takes everything out. It could make a new vector, whatever. But this will work nicely. And technically, this also might make more sense here. So it's kind of like after I finish updating the velocity, then I can reset the acceleration in case there's other things at play. So now we can see both cohesion and cohesion and alignment are at play. And look at this. Eventually, they're just all going to become this one clump. Come on, you can catch up. You got it. Go, go, go. Go, catch up, catch up. Yeah, one clump. Okay. One thing I would like to do, I really want to attach sliders to those parameters, but I got to resist because we got to add separation. Okay, we've got alignment and cohesion. Separation. This one's a little bit hard. Let's look at it. Wait, come on, scroll. Steer to avoid crowding local flock mates. Steer to avoid crowding local flock mates. Okay, so we have the idea. Where's my eraser? Here it is. We have the idea of a local flock mate. Let's kind of erase this for a second to just deal with two. Here's me. That's me. Here's my local flock mate. If this local flock mate is too close, it's within some sort of distance threshold, I want to steer to avoid that. What would be my desired velocity? My desired velocity would be to move in the opposite direction. So the idea is my desired velocity is in the opposite direction. But what if there is one here? My desired velocity would also be in this opposite direction. So then my net desired velocity would be the average of these two. And it even would make sense for the magnitude of that desired velocity to be proportional to the distance. So if this one is here, I maybe want to avoid it, but I only really need to think about avoiding it a little bit. If this one's really close, I need to avoid it a lot. So the magnitude of the vector is inversely proportional to the distance of the local flock mate. And so this might end up with kind of like a desired velocity of something like this if I'm averaging those two together. Okay, so let's see if we can implement that. Not going to be super easy, but let's do it. Okay, so the nice thing is I'm going to start with cohesion because we've kind of, cohesion is close to separation. And again, boy. I will refactor this later, you know. I will refactor this later. I will refactor. I should show you that I'm wearing my I will refactor this later t-shirt, by the way. Okay, so separation. So I'm going to leave this at 100. Steering. Oh, I think I might need to use more, like I kind of like the idea of just having one vector that ends up as, it's sort of the average here, then it's kind of like the difference, but I think I need to think, let's, one step at a time. So I'm creating this vector. So this is the same. If it's not me and it's within the perception radius, what do I need? I need a vector, I'm going to call it difference, which is the others, I want a vector, that points from, I want a vector that points from the other to me, because I want that to go in the opposite direction. So it's my position minus the other. So I want a vector, a new vector, which is the subtraction between my position and the other's position. So this is a way of calling the subtract function, which doesn't operate on a vector, but subtracts two vectors and gives us a new vector, which is difference. Then I want the difference to be inversely proportional to the distance. So I'm going to multiply it or set its magnitude, something like that. I mean, this is making it, I'm going to divide by distance. I could just say divide by distance, right? It's inversely proportional. The farther away it is, the lower, the higher, the farther away it is, the lower the magnitude. The closer, the higher the magnitude, okay? And the distance, I guess technically that distance could be 0, and that would be problematic. But with floating point math, we're almost never going to get a value of 0. Okay, then I want to add, then that is the thing I add up. That's the thing I want to average. All of those vectors that are pointed away from the things near me. I think we're actually in pretty good shape here. This isn't as hard as I thought. This was the tricky part here. So get a vector that's pointing away from the local flock mate, make it inversely proportional to the distance, add it up, then this is the same. Because, oh no, I don't need to subtract position. I kind of don't know if I want to. So let's leave this whole always go at maximum speed thing. And then the rest is the same. The rest is the same, right? Once I have that, just average it, set it to max speed, subtract out the velocity, and limit it to maximum force, and that's the end. Okay, so let's see. So now, just to be sure that this is right, pause for a second. Okay. Just to be sure that this is right, let's go into Boid. Let's go to flock. Let's add that separation equal this dot separation, and then let's add in separation. And I want to not bother adding cohesion and alignment. So I just want to see separation right now. Oh, and William in the chat is saying 1 divided by distance squared maybe. That's probably a good idea. Squaring the distance to make it quadratic or whatever, that's probably smart. I bet you if you read this full explanation, it does something like that. But let's just see. So are these separating? Yeah, it looks like they are. It looks like that when they get close to each other, they're kind of moving away from each other. Weird behavior. This doesn't look exactly like what I expected. Let's give the maximum force, just really let them be super strong about separating. Yeah, there we go. Okay, so that's more like what I expected. That's way too strong. Yeah. Why do they feel like they're... Something is weird here. I think my inversely proportional thing is wrong. What's going on? Let's go back to separation. Where is it? Here it is. If distances, let's give it a much smaller perception radius. Oh yeah, no, this is what I expected to see. Oh, its perception radius is 100, and there's just so many of them that they can't all separate. This is what I expected to see, and I think it wasn't really a bug in my code, it's sort of a bug in my conceptual sense of how this works. And also maybe the inversely proportional thing. So a couple things that I might do here is what if I take this out? And then also let's try dividing by distance squared. I kind of like that idea to make that, whoa. That's weird. That makes them want to stop. Is that because, because their desired velocity ends up being, oh yeah, it actually has to be maximum speed. Because if in other words, if their desired velocity is I'm far enough apart, my desired velocity is now 0, then it's going to make me want to stop. Yes, because I'm always returning an empty vector. What I could do is instead of returning an empty vector, I return a null vector and don't bother adding that as a force. But that all aside, let's leave it at this. So many ways you could change or alter this, that this is pretty good. This is what I wanted to see. This is separation only. So now we should be able to see, and let's, I'm going to do this really quickly. I'm going to not be thoughtful at all about the interface, but just so I can debug this effectively, I am going to go into sketch.js. I am going to say let align slider, cohesion slider, and separation slider. And I should use, and I'm just going to say align slider equals create slider. And I'm going to give it a range between 1 and 5 with, and actually let's give it a range between 0 and 5 with a starting value of 1 and increment value of 0.1. So I want to do this for all of these sliders. Cohesion slider, separation slider, and then in Boid, I want to say, where I calling flock, I want to just scale them. So I'm going to say separation dot multiply separation slider dot value. And then I'm going to do this also for cohesion and for alignment. It doesn't really matter the order, but I probably should be consistent just for just going to always, the order doesn't matter at all, but so this is separation slider, align slider, and cohesion slider. Are those the names? So again, I'm not thinking about design or interaction design or visual design or any of that. Just wanted to quickly put 3 sliders in there. And now, so by the way, flocking. So this is now the flocking simulation. I didn't draw them as triangles. They're not rotating, but this is the flocking simulation. But just for the sake of argument, this should be, what order did I make them in? They're not labeled. Alignment, cohesion. So I want to do, alignment, cohesion, separation. That's the order that I thought of them in. So let's just turn all the way up separation. Oh boy. Let's turn off. Right? This is only separation. Now turn that off. let's turn on only alignment. Whoa, wait, no, that's, oh, the alignment is so strong. When the alignment is so strong, it makes them like go in circles around each other. I'll talk about why. So let me just decrease those ranges. So there's a little bit of an issue here, which is that, so let me explain to you why that happened. Why did that happen that they were twirling in circles? Well, look at this. I'm updating them one at a time. And the next one is flocking with the previous one's updated value, right? Instead of taking a snapshot of all their current velocities, and then each one updates based on that snapshot, I start with a set of velocities. I update the first one based on that set of velocities, and now its new velocity is there. So in the next one, it's actually updating itself based on the previous one that I updated, which is not how the world works. It's not how time works. But that's causing them to like ripple into each other based on the order and go in circles. That is something that you might want to consider fixing. I'm not going to fix that. But now I can really play with these. I can get different sort of qualities of flocking based on how strong I make these rules. So no alignment, a lot of cohesion, no separation, add a lot of separation, less cohesion. I mean, separation I shouldn't make too strong, but it's important. And then let's add some alignment back in. And there we go, flocking. Whew. Okay, this coding challenge is complete. It is done. I will be uploading the code. You will, if you want, you can look in the video description to find the code as a snapshot as exactly what it is. Let's though make a list. Let's make a list on the board of things you might try to do. And I'm going to take suggestions from the chat and make your own version of this. And you can hashtag coding flocking, coding train flocking, I don't know. But let me make a list of some things you might try. Number one is oh, shoot. Okay, hold on, time out. Mathieu will edit this. I'm throwing away these markers that don't work. I'm in the hallway. There we go, okay. All right, number one, snapshot of all velocities. That's going to be my code for that. Number two, an optimization you can do is called a spatial subdivision or a quad tree optimization. One of the things that makes this really slow, and I'll just show you here for a second, is if I were to try to do this with 1,000 Boids, right? Look how slow this is. But you have to realize it's not a big deal for P5 to draw 1,000 things moving. Why? It's fine drawing 1,000 things moving, but as soon as I put the flock function in, it's super slow. The reason that is because it's got to do an every Boid check every Boid against every other Boid check. And so there's a way of subdividing the spatial subdivision, into bins or buckets and have the Boids only check ones that are near each other in the same buckets. And that's called, I probably have a lot of the distance calculation. I could reduce the number of times I call it. But for this, quad tree or just simple spatial subdivision. So these are things you could try. These are just code refactoring, really, actually. The other thing you could try, another thing you could try is, hold on, sorry, I lost my train of thought. Because it was related to this spatial subdivision thing, optimize. Well, maybe there's some suggestions in the chat right now. Add attractors or trees, multiple, yeah. Fix the velocity snap trapezoid, make Boid. I'm just looking at the chat. Wait, I had something in my head that was the third thing. Snapshot of all the velocities, optimize quad tree and subdivision. Oh, yeah. I said reduce the distance squared. Whatever. Okay. Another thing you could try to do is really build a more sophisticated interface. And there's lots of other parameters that you could control and try, right? There's the perception radius. So we saw that you could change the weights to the weights for alignment, cohesion, and separation. But there's also the perception radius. There's maximum maximum force, there's maximum speed. You know, each rule could have a different perception radius. So many possibilities. So this is the stuff that you could do to like really control and tweak all the values and play with it. Another thing you could do is just design, visual design. Like, are they triangles, circles? Are they flapping butterflies? Like, how do you design of the Boids? Like, make your own beautiful visualization of how you design and draw them. Tadpole-like, there's so many ideas there. Another thing you could try to do is 3D. Can you extrapolate this into 3D? And if you see the word quaternion anywhere you start to research, you might want to turn back. But you could extrapolate this into 3D. I'm going to look. There were some interesting suggestions. Oh, right, Boids with different parameters. Yeah. So another suggestion which came from the chat, thank you, is Boids with different parameters, right? So there's no reason why every Boid has to have the same max speed or maximum force. They could have or same perception radius. You could implement this thing called the view rule, which is kind of interesting to think about. I don't know why, I'm going to show, I have a diagram of it, but it's one of the things that right now is each Boid, there's two things about this. One, each Boid can see everything around it. But what if the Boid itself could actually only see, if it's moving in this direction, things that are within its particular view in front of it? Maybe it doesn't deal with anything that's behind it. Doesn't try to use cohesion or alignment or separation. And then the view rule, which is posited by Flake in the book, The Computational Beauty of Nature. I'll link to that book also. It's a wonderful book with tons of, probably like 90% of the things on my channel are all from the Computational Beauty of Nature book. But Flake posits this additional rule that you always want to keep your view empty. So if there is a Boid in front of you, you want to steer that way to keep your view empty, clear, and this might result, the theory is that this will result in something that looks more like that pattern that you'll see of actual birds flocking, where they kind of appear almost in this triangular pattern. So what's interesting about this, right, you see a pattern like this, you think, aha, this is a top-down behavior. There is a leader, this bird, who is saying to all the other birds, fan out for me and follow me. But yet, this type of intelligent behavior, emergent phenomena, can come actually only from simple local rules of interaction. And this, by the way, this is what this whole video is about, if you didn't gather that already. Okay, what are some other ideas? Other ideas might be, whoops, hold on. Other ideas might be adding obstacles, other forces. There's, thinking about these, living in a world where they're interacting with other things. Maybe there's a predator that comes in and is chasing them. All sorts of unique and interesting possibilities. Okay, so thank you everyone for watching this coding challenge. Put your other ideas for things people could do in the comments. And then if you make your own version of this flocking code, please go to the codingtrain.com challenge page and submit a link to what you made. I will also make a version of this that runs in the web editor and link to all those resources like the Craig Reynolds original paper about flocking, the video on YouTube, and the chapter in my Nature of Code book, okay? Thanks for watching this coding challenge, flocking, and I'll see you soon. Okay. All right, everybody. Oh boy, it's 12:30. I definitely have to go. I'm glad that I fit in this extra coding challenge, and I'm actually recording it to disk, so this can be edited. I assume this is at least an hour, right? But hopefully this was useful. Thank you, all of these nice comments. So when will I be back? A week from tomorrow, if I have to guess. So there will be no live stream tomorrow. This was today's Coding Train episode. The next time I will be back is a week from tomorrow, next Friday. Upcoming soon is a live stream from the ITP Winter Show. If you're in the New York City area, I highly recommend you come to this. This is the show of students' work. at ITP Sunday, December. I'll probably do a live stream from the show in the afternoon of Monday, December 17th. And then later that week, hopefully on December 20th, I'm going to do a fundraiser telethon for the Processing Foundation, but I got to figure out this super chat thing. So that's that. What else do I want to tell you? If you live in Europe, possibly in France or near the city of Paris, coming soon, I'm hoping to announce a workshop/meetup that I'll be doing in Paris in early January. So I don't want to say anything more about that because it's not settled. I don't even know exactly which date yet. But stay tuned. I'll announce it on Twitter. I'll mention it again here. But that I'm hoping to have that, which is the first ever possibly obviously I go to things and I've met people. Oh, I do like being in my own little room here. No, I don't like that it has no windows though. But anyway, but this is exciting to me to try that, especially I get to practice my terrible, terrible French. All right. Perfect time. Yes, Alka. Okay, let's talk offline, Alka, about your suggestion to fly to New York City to help with the live stream for the event. I actually am this is something I would seriously take under consideration. Okay. Welcome new member, Motion TX. Thank you, new member. Wait, I want to figure this out. There's a way that I can make a page. I have to log into my other. I guess I can't. I want to make a pop-up thing happen when I get a new member. Infor Math Music says workshop in Paris. I live in Paris. Excellent. I would love to go everywhere, frankly. Traveling is hard and expensive and uses a lot of energy. Both the world's energy and my own energy, and I have these small children that I spend a lot of time with, and a family, and so I can't really just go everywhere, but I dream of going everywhere. I would really like to go to Japan. I'd really like to go, I've never been to anywhere in the Middle East, never been to Japan, never been to Africa. I've never been to Australia, New Zealand. These are just things that are popping up. I've been to a lot of places in Europe and Canada. I've been very, very few places in South America, so I don't know. World Tour, Coding Train World Tour coming soon. Thanks everybody, and Infor Math Music, if you come to the meetup, you will see me. I will be bringing my stickers. I will be bringing the Coding Train stickers. Thanks everyone, and yeah, Norway. I have been to Norway. So Elo Lee is just saying, can I tell you about my favorite place, one of my favorite places in the world? Runda, Norway. This small island off the coast of Norway called Runda, which I believe means bird island, is one of my absolute favorite places. At certain times of year, you can go see the puffins. I went on this 6-hour hike, it wasn't really 6 hours, really long hike all the way to this lighthouse that you can only get to by hiking, and then you can just sleep there overnight. We hiked back, but this place is amazing. I really want to go back there. There's a center there, which is like a bird science site. Anyway, if someone can figure out a way that we can do a live coding train from the island of Runda, that would be awesome. Dominican Republic, that would be Brazil, all these amazing places all over the world. Here's a nice picture of Runda. It was, where did I stay? I stayed at the bird center there, environmental center, yeah, research station. So I stayed here. You can actually just stay there. It's for scientists, but you can also just book a room there because I am not a scientist. The Runda Environmental Center is a research station with 4 main activities. Oh, this is perfect for flocking. Let's look up, actually I was in a Norwegian, I'm not kidding, if anybody can find this, I have it buried in my computer somewhere. I'm in a Norwegian travel magazine with my family because they were there shooting photos to be I think it was a travel magazine, and we were the only people staying on the island because it was kind of the wrong time of year to visit. There were no puffins. Runda, Norway, puffins. It's near Aalesund. So yeah, these are the puffins of Runda. And yeah, right. It's very. I see these photos and I'm terrified because there's also these cliffs you can go right up to the edge, and I feel we were doing that. And I think about it and oh my God, were we doing something really dangerous? This place is amazing. Coding Train is sponsored by the Norwegian Travel Council. No, not at all. But it's very expensive in Norway. I mean, I think I don't think. Hopefully, it's not for people who live there because they have excellent. Services, healthcare and those types of things. But as a tourist there, it's incredibly expensive. Food was, so that is. And I don't know, I have to say, I didn't love the food in Norway. I mean, actually I had some really interesting things to eat. And I spent a little time in Oslo, and there were some like really awesome restaurants there. But we went, because it's just, I don't know, maybe it's hard, like it's like dark and wintry. I love you, Norway. All right. I think, by the way, the author of the I Will Refactor This song is Norwegian. All right, I have to go. I'm like super late. All right, goodbye, everybody. Please refactor my flocking code. I got to get it in the editor under the Coding Train account soon. This challenge will probably be up edited next week sometime. And I will see you. I am going to stop the live stream on this page. Where is that page? Shoot, I don't have it open. Oh, wait. No, it's a live control room. One thing that by the way, one thing that I'm planning on doing, MPJ gave me this idea. I mean, I could have thought of this myself, but lots of people do this, is getting a loop for like stream about to start, loop for thanks for watching, and like a loop for like be right back, like fun little Coding Train animation thingies. Anybody wants to make some of those? I mean, I would be glad to hire somebody. And Mathieu, who does video editing, has a lot of talents and might be interested in working on this. I don't mean to ask for things for free, but if you're interested, if you're an animator and you like rainbows and coding stuff, and you want to help me make some crazy interstitial stuff that I can put in Open Broadcast Studio, get in touch. Okay, stop streaming, and I'll see you all later.